Okay, in this chapter, we're going to look at some synthesis examples using some of the reactions that we've learned this chapter. Okay, so first, just some tips on attacking synthesis problems. I think one question you always want to ask yourself when you start a synthesis problem is, did the carbon skeleton change? Because we only know a couple reactions so far where we can change the carbon skeleton, right? If it gets bigger, in this chapter we've learned the Grignard reagents, and then last semester we learned about terminal alkylation and Gilman's reagents. If the carbon chain gets smaller, I think the only ways we've really learned to do that so far are from last semester, and that's oxidative cleavage. Right? It's often very helpful to work both backwards and forwards. The book talks a lot about retrosynthetic analysis. I don't follow that exact procedure, but I do often use my products and take a look at those functional groups. And sometimes there are only a few ways to make those functional groups, and so that can give me an idea of how to proceed. And so I often work both backwards and forwards on these synthesis problems. This is something I mentioned last semester. There will often be more than one reasonable synthetic pathway. Now, last semester, we didn't know that many reactions, and so very often, there really only was one good way to do or to accomplish a particular synthesis. I think the more reactions we learn, the more it's going to be true that there's more than one good way to approach that synthesis. I would also highly recommend, even if you don't read the book a lot, read this section in chapter 12 from the textbook and work through the examples that he gives. I think the more perspectives you can see on these synthesis problems and the more advice you can get from different sources, the more that will help you. And then, really, in order to be good at these synthesis problems, you've got to learn the reactions. If you don't learn the reactions, then you're kind of dead in the water. And then it's also key to practice. Do a lot of practice problems. You'll start to see some patterns kind of repeat themselves over and over again. So that when you see those on the quizzes and the tests, you'll sort of have a head start. All right, so I'm not going to go through this whole figure. I just wanted to kind of give a shout out to this figure in the book. This is figure 12.11. In this figure, the textbook author sort of highlights a lot of the key reactions that we've learned so far and different ways of transforming between the different functional groups that we've learned so far. So I highly recommend take a couple minutes, either pause this video, or if it's too small, go to this figure in the textbook and study these reactions on your own. Okay, so here's our first example. And I picked this example to highlight the fact that there's often more than one pathway to achieve these syntheses. And I think, so we've learned some reactions in this chapter that we could do this synthesis with, but we could also do this synthesis entirely with reactions that we learned last semester. And so let's approach it that way first. Right, so last semester we only learned a couple ways to make a ketone. Right, so one was through oxidative cleavage, but my carbon skeleton didn't change. So I'm not sure I want to go the oxidative cleavage route. The other way is if I start with an alkyne, hydration of an alkyne can give me a ketone. And so if I am able to get to this alkyne, I can use H2SO4 with water and then mercury sulfate as a catalyst to go from this alkyne to this ketone. So then I need to get from this starting material to this alkyne. And so not only does this example show how there are multiple pathways, but it also shows how oftentimes I work both backwards and then forwards. So the way that we know to make an alkyne is to start with a dihaloalkane and then do a double elimination. So to do that from this alkene, I first need to put two halogens on. And so the way to do that would be to just add Br2 or Cl2. And so that'll give me and I'll be consistent with the stereochemistry, even though it's not going to really matter because we're going to kill the stereochemistry as soon as I turn that into an alkyne. And so then to convert this dihaloalkane into the alkyne, I'll use excess NaNH2. And because it's going to make a terminal alkyne, I'll need to add water to put that hydrogen back on in the end. And so I think this pathway, convert the alkene to the dihaloalkane, do the double elimination to give me the alkyne, and then I can use hydration of the alkyne to give me the ketone. Now, in this chapter, so if we attack this from another way, also kind of working backwards, another way that we know to make the ketone is through oxidation of an alcohol. And so if I'm able to make this alcohol, I can turn that into the ketone through oxidation. And so if we use chromic acid, so we could use sodium dichromate, and sulfuric acid and water, that will convert this alcohol into the ketone. And so then I need to convert this alkene into this alcohol. So I want Markovnikov addition, because I want to put the OH here. But if I just were to use H3O+, I would get carbocation rearrangement, because this carbocation is more stable than this one. And so that would put the OH here, which is not what I want. So to avoid carbocation rearrangement, I want to use oxymercuration demercuration. So the oxymercuration demercuration will put the alcohol where I want it, and then I can use oxidation to give me the ketone. So there are two perfectly good pathways to achieve this synthesis. Okay, in this example, again, let's double check our carbon skeleton. So I've got 4 carbons with a methyl coming off carbon 2 from the right, 4 carbons, a methyl coming off carbon 2 from the right. So my carbon skeleton didn't change, but I have moved the functional group. It went from being on carbon 2 from the left to being on the end. And last semester, I think we learned that in order to move functional groups, we often took advantage of a combination of elimination and addition reactions. Right now, in this case, I'm going to, I think, kind of work forward. We've learned a number of reactions where the ketone is sort of the end point, but I think the only reaction that we've learned so far where the ketone is a reagent is in reduction of a ketone to form an alcohol. Right, and so then if I end up with an alcohol here, then I want to do an elimination reaction to put a double bond here, and then I can do an addition reaction to put the OH on the end. Right, so we can kind of work backwards if we want. So I know my goal is to get this alkene. If I can do that, then I can use hydroboration oxidation to put the OH on the end. And then I know I need to reduce this to turn it into an alcohol. So we've learned a couple reactions for that. I'm going to use lithium aluminum hydride. And I need to add water in a separate step. Right, if I was using sodium borohydride, I could have just done the water in the same step. But with lithium aluminum hydride, I need to add the water in a separate step. So that's going to reduce that ketone to give me the alcohol. And then I want to put the double bond here, right? So if I was just to use sodium hydroxide or sodium ethoxide, that would give me the more substituted alkene. So I want to use a bulky base to put the double bond here. Right, another way I could do elimination is with concentrated sulfuric acid. But concentrated sulfuric acid, there's no way for me to control the regiochemistry. So that's going to put the double bond here as well. But OH is a bad leaving group, so I can't just react this with the tert butoxide. I've got to turn the OH into a good leaving group first. So I'll turn that into a tosylate. So we'll do TSCl and pyridine, and then That'll convert the alcohol into a tosylate. Then I can use the terbutoxide to give me the less substituted alkene. And so I think this combination of steps will achieve the synthesis that was requested. Okay, so one more example. So I think in this case, right, again, we want to check and see if our carbon skeleton changed, and in this case it did. Right, so I started with 4 carbons, and then in my product I've added this ethyl group. Right, and again, kind of working backwards. So I know my carbon skeleton changed, so we could use terminal alkylation, we could use Gilman's reagent maybe, but the presence of the OH makes me think that probably the best way to go is to go with the Grignard reagent, right? In the Grignard reagent, if I react that with a ketone, that'll give me an alcohol. So the fact that my carbon skeleton changed and I have an OH, that leads me to lean towards that method. So if I can get this ketone, and then I react it with an ethyl group attached to the Grignard reagent, that will give me this product. So then my goal is to get from this starting material to this ketone. So again, we know a couple ways to get to a ketone. I can either go through oxidation of an alcohol, or I can go through hydration of an alkyne. Now, it would be nice if I could just go directly from this to an alcohol with a substitution reaction, but I don't think I can do that. Right? If I just react this with NaOH, the problem is, if you remember back to that chart that tells us whether substitution or elimination is going to be favored, if I have a secondary substrate and then I use NaOH, which is both a strong nucleophile but also a strong base, a secondary substrate is going to prefer elimination. And so I'll get some OH, but that's going to be the minor product. And we're doing synthesis. We don't ever want one of our steps to be the minor product. So another way to get to an alcohol would be to go through elimination and then addition. So if I just use NaOH, that would put the double bond here. And then I could add, right, it's a symmetric double bond. And so then using acid catalyzed hydration, I could put the OH on. But I'm also going to get some OH in the first step. And so I think what I'm going to prefer to do is I'm going to use terbutoxide. That's going to put the double bond here. But the advantage of this is not only do I have a secondary substrate, but when I use this bulky base, this is going to ensure that I only get primarily the elimination product. So that'll give me this product, and then to get the to get an alcohol, I don't have to worry about carbocation rearrangement. So I can just use acid catalyzed hydration. So I'm going to use H3O+. You could use dilute H2SO4 instead if you wanted. It's going to be the same result. So that's going to give me this alcohol. Of course, I'll also write it. I do have a chiral center, and I'll get the enantiomer, but as soon as I turn that into the ketone, that's not going to matter, so I'm not going to show the stereochemistry in this case. And then I can get the ketone with by oxidizing my alcohol. So previously I used chromic acid, so this time let's use the Swern oxidation. So for that, I'll need to use DMSO and this COCl2. Sorry, the 2 is outside the parentheses. And then triethylamine. So I think this will complete the synthesis. So we're going to use terbutoxide with a combination of a secondary substrate and a bulky base. That's going to ensure that I primarily get almost all the elimination product instead of a mixture of elimination and substitution. I can then use acid catalyzed hydration to put the OH on the more substituted carbon. I don't have to worry about carbocation rearrangement. I can then oxidize my alcohol to the ketone. In this case, we're using the green Swern oxidation. And then in my final step, I can use the Grignard reagent to convert my ketone into an alcohol, and at the same time add this ethyl group from the Grignard reagent.